Imagine boarding a flight in London as the sun comes up and arriving in New York before it even rises there. That is the reality of moving faster than the rotation of the Earth, landing at a local time earlier than the moment you departed. In the late 1950s and early 1960s, the aviation industry didn't view this level of speed as science fiction. Commercial supersonic travel was widely accepted as the guaranteed inevitable next step in human progress. Four global powers immediately locked into a high-stakes race to cross this threshold first: Great Britain, France, the United States, and the Soviet Union. The Soviets actually made it to the skies first with the Tupolev Tu-144, but their rush to beat the West resulted in a highly inefficient design, plagued by deafening cabin noise and fatal crashes, most notably at the 1973 Paris Air Show, which severely cut its passenger lifespan short. The Americans, meanwhile, threw their weight behind the massive Boeing 2707. However, as public protests over the extreme noise of the sonic boom grew louder and development costs spiraled out of control, the U.S. Congress quietly canceled all funding before a single prototype was ever built. That left Britain and France. Realizing the sheer financial weight of developing a supersonic transport alone, the two governments signed a historic treaty in 1962. They completely merged their independent design studies, pooling their national budgets to tackle the problem together. With the Americans out and the Soviets stumbling, the Anglo-French alliance stepped into a clear vacuum. They were determined to build their machine at all costs, setting the stage for a massive engineering war against the physical laws of aerodynamics. The first hurdle was air resistance. Engineers had to design an airframe sleek enough to pierce the massive drag of the sound barrier at 1,350 miles per hour. But that same shape still needed to generate enough lift to safely glide down to a runway at low speeds. This schematic shows their solution, the ogival delta wing. Unlike the straight wings of standard commercial jets, this gracefully curved double delta shape sliced efficiently through supersonic air, while still creating the necessary lift for landing without the need for traditional flaps. But that wing shape created a dangerous blind spot. To generate lift during a slow approach, a delta wing forces the aircraft to pitch upward at an incredibly steep angle. Because of this posture, the physical nose of the airplane completely blocked the pilot's view of the runway. The fix was purely mechanical. They built a hydraulically actuated nose cone that physically drooped downward by 12.5 degrees, moving completely out of the way so the flight crew could see to land. Pushing a passenger cabin through the sound barrier meant the alliance had to discard the traditional architecture of an airplane entirely. And once they solved the air resistance, they hit the thermal barrier. At Mach 2, atmospheric friction violently baked the exterior of the aluminum airframe, driving temperatures up to 127 degrees Celsius. Taking a look at this side profile vector, we can see the terrifying consequence of that heat. The intense temperatures caused the entire fuselage to physically expand and stretch by up to 10 inches in mid-flight. As the metal expanded, the aircraft's center of lift shifted backward toward the tail. To keep the plane from tearing itself apart, engineers designed an automated system that continuously pumped heavy aviation fuel between the forward and rear trim tanks. By shifting liquid weight toward the back of the plane, they realigned the center of gravity on the fly. Supplying the raw power to achieve these extreme speeds were four massive Rolls-Royce Olympus 593 engines. Derived directly from military bombers, these turbojets used afterburners to aggressively punch the aircraft through the immense drag of the transonic zone. By engineering their way past these violent physical barriers, the alliance succeeded. They built a commercial airliner that carried civilians while operating with the extreme structural tolerances of a military fighter jet. Yet the exact brute force engineering required to conquer the laws of physics ended up generating real-world headwinds that Concorde could never outfly. Looking at this route map, you can see the immediate impact of the environmental barrier. Breaking the sound barrier produces a highly disruptive, earth-shaking sonic boom. In response, governments around the world strictly banned Concorde from flying supersonically over land, instantly erasing the vast majority of its flight paths and confining it almost entirely to transoceanic tracks. Then came the economic reality. To maintain Mach 2, those four massive Olympus engines consumed roughly 4,800 gallons of aviation fuel every single hour. Following the oil crises of the 1970s, the price of fuel skyrocketed. Operating an aircraft with such immense consumption rates became incredibly expensive, forcing ticket prices into the thousands of pounds and limiting the passenger base to a very wealthy few. Between the restricted flight paths and the exorbitant operating costs, the aircraft's market potential collapsed. What was supposed to be a global transportation standard shrank down to a hyper-exclusive novelty. Ultimately, only 14 Concordes ever entered commercial passenger service. The fragile operation reached its tragic tipping point in July 2000. During takeoff from Paris, Air France Flight 4590 struck a piece of metallic debris on the runway, rupturing a tire and puncturing a fuel tank. The resulting crash killed all 109 people on board and 4 on the ground. It was the only fatal accident in the aircraft's 27-year history, but it grounded the entire fleet for over a year. The planes did eventually return to the skies, but the aviation landscape around them had moved on. Facing a post-9/11 travel slump, escalating maintenance costs of aging airframes, and a lack of replacement parts, British Airways and Air France permanently retired the fleet in the fall of 2003. Concorde remains a magnificent paradox. The engineers successfully solved the absolute physical limits of supersonic flight, but the aircraft was ultimately defeated by the uncompromising realities of modern economics and environmental impact. Today, these airframes sit quiet in museums, a static monument to a brief time when humanity decided pure speed was worth the cost.